Okay, thanks for introducing me. I'm Mariano. This is a joint work between Eurecom, Symantec Research Labs, and University of Milan. And today in this research, I'm going to talk mainly about the analysis of sandbox datasets. So let's start. In the past decade, many security researchers have collected and then analyzed a large number of malware samples. This number is in the order of tens, even hundreds of millions of unique malware samples. Researchers generally, I've published many papers, reports, and statistics by using this dataset. But then we all know that the vast majority of these samples is not really interesting, because, for example, they contain many polymorphic variations of the same known samples. So in this talk, we're gonna have a look at one of these sandbox datasets. In particular, we will inspect the Anubis sandbox dataset. Anubis is one of the first online sandbox that was available online. And what we notice is generally that okay, if you look closer at this dataset, you can find some really interesting cases. For instance, most of the famous samples used, for example, in APT campaigns have been submitted sometimes in a really weird situation from some, for example, from some DSL residential networks, and have been submitted months and even years before they were detected by antivirus companies, and APT campaigns has been publicly disclosed. For instance, one of the samples of the APT1 campaigns has been submitted 43 months in advance to our sandbox before the Mandiant report. Second, we also notice a continuous interaction between the malware authors and our sandbox. So we decided to manually look at some of these interesting cases. And what we discovered is that most of the cases, the malware authors are just developing new evasion techniques. And in other cases, they are just testing some, for example, suspicious programs. Additionally, we also talked with some other sandbox maintainers, and they confirmed that they observed more or less the same behaviors on their sandbox datasets. So, starting from these observations, we wondered if it's possible to design a system that is able to automatically detect these malware developments inside the sandbox datasets. So we devised the following systems that is composed by many components. The first one is the filtering part. In the filtering part, we filter out all the irrelevant samples. Then we cluster the interesting samples via binary similarity. Then once that we have these clusters, we inspect samples by samples with some fine-grained binary analysis techniques. Then by using we extract many features coming from, for example, the static analysis, the dynamic analysis, the submission metadata, and also from some external feeds like virus totals. So, and then we collect all these features, and then we train a classifier, and thus we run some machine learning algorithms. So now, in the following slides, now I'm going to introduce every component in details. So our initial dataset is composed by over 30 million of samples. So before performing any analysis, we want to reduce the amount of information that we need to process. Okay. For this reason, we decided to filter out all the samples that are not strictly related to malware development. To start with, we filter out all the samples that have been submitted from batch submissions, coming from, for example, from security companies and research centers. So in this way, we take only the submissions coming from individual users. Then we decide to remove all the samples that, even if they have been submitted by an individual users, they are not. They have been observed before in our sandbox. For example, the submission was coming from a big submitter like a research center. Then we decide to filter out all the samples that, even if they have been submitted by an individual users and have been observed for the first time in our sandbox dataset, they have been observed, for example, before by VirusTotal, and for example also by an antivirus company, in our case Symantec. So at the end we have more than 214,000 unique malware samples. And this is our, let's say, final dataset of the reasonable candidates. The reasonable candidates for malware development, because they have been submitted by individual users, they have never been observed in the wild, and they are unknown from security and antivirus companies. But in order to simplify our job, we decide to filter out, also the packet binary. We decided to do this because since we need then to apply some static analysis techniques, and then more importantly, we want to double check our results. So we take the decision to filter out the packet binary. But I will get back to this point later in my presentation. Then the second step is the clustering part. The main goal of the clustering is to group together all the samples that are related to possible malware development. For this goal, we use an agglomerative clustering that is mainly based on the binary similarity part and some submission metadata. For the binary similarity part, we use a tool like SSDeep that is implementing some fuzzy hashing techniques. And for the submission metadata, we mainly rely on the submission time, because we want to extract, for example, the timeline, the submission timeline. Then we want to reduce the number of comparisons because we have many samples. And for this reason, we decide to have a sliding window of 7 days. Then in order to ensure the binary similarity, we decide to take a similarity threshold for the fuzzy hashing algorithm of 70%. This threshold has been proven by previous research to be the optimal threshold in order to minimize the number of false positives. So after running the clustering, we obtain almost 6,000 clusters containing on average 4.5 elements each. Then the next step is the fine-grained binary analysis. So let's imagine that we have the clusters depicted on the left of the slide. And this cluster is composed of 4 nodes. Every node, of course, every node represents a sample, and every edge represents the similarity. Then, first of all, we first normalize the assembly code of each sample. We just normalize the operand in this case. Then we extract the timeline of this, for the submission time. And and sample by samples, we compare the samples using binary diffing techniques. And first, we start by inspecting the call graph. If we find there a mismatch, then we literally zoom and we have a look at the control flow graph. So we had a look at the basic block level. Then we extract there is the step for the feature extraction that is composed of 2 phases. The first one, first we extract the features for the samples, and then once that we have the samples, we try to aggregate these features and we extract the features for a single cluster. So the samples features, they are grouped by 6 categories containing for a total of 25 features. We have categories like the file features, then the timestamps, where the timestamp is really important, for example, when doing an investigation to extract some intelligence like the submission timeline. Then we have the antivirus features coming from external feeds like VirusTotal. Then we have the user-based features because Anubis allows the user to submit the samples from a web interface. So we can extract main information like the user agent or the IP address of the submitter. Then we use the binaries features coming from the static analysis phase that I previously described. And then we have the behavioral features that are coming from the dynamic analysis. So they are coming from the report generated by our sandbox. Instead, for the clustering features, we try to aggregate all the features of the samples and then to create some interesting features that are just for the cluster. Some of these interesting features are, for example, the shape of the cluster that is really interesting. And in this way, for example, we can extract some interesting patterns and in this way extract some interesting clusters that are possible, for example, for development. Then another interesting feature that coming from the cluster features is that, for example, we can have a pattern like we can extract, for example, all the clusters in which the first samples, for example, are completely unknown to any antivirus companies, and but the last one is known and is labeled as malicious. And this is, of course, a good indicator for a cluster that is a possible development or at least is worth having a look. Then also another interesting feature here, another possible pattern is the possibility to, for example, to extract all the clusters in which the first samples have a really complex behavior, and that you can serve, for example, on the analysis report, but the last samples of the cluster has no behavior at all because probably is implementing an anti-sandbox check, so after a few seconds is quitting the execution. Then the last step, once that we have extracted all these features, we have the machine learning component. We test many machine learning algorithms, but we had the best results with the logistic model tree. The logistic model tree is a combination of the decision tree plus the logistic regression. In this way, we can build a decision tree in which the leaves have a linear regression models. But here, the logistic model tree is a supervised algorithm. So we need our ground truth, we need our training set, and this is the real challenge for us. We need to label manually our data set. So we randomly choose 200 clusters, and at the end of the manual analysis, we were able to flag 91 clusters as a non-development and 66 clusters as a development. The remaining clusters, we were not 100% sure because in some cases it's really difficult to decide when is development and when is not, even for an expert reverse engineer. Because if you imagine, for example, when you have a small cluster, for example, of 2 samples, when you have a small cluster of 2 samples and you start doing some binary diffing techniques, it's really difficult when you have, for example, just 2 different functions to understand if it's a development or if it's just a simple variation. So once that we run our classifier on the whole dataset, and this is our results. We had more than 3,000 clusters as a potential development, and roughly the 50% of these clusters were considered malicious. So this means that at least 1 sample is known by antivirus companies there. Then these malicious clusters is detected on average in the wild by antivirus company after more than 100 days. And generally, these malwares has been detected all over the world on more than thousands of computers. And let's say that the malware natures of these samples is ranging from all the kind of malware families like Trojans, backdoors, and even keyloggers. Then now I will present some interesting examples that we were able to find manually through our algorithm. The first one is about the development of an anti-sandbox technique. So if we have a look at the timeline, Here we can see, okay, first of all, our cluster is composed of 3 samples. If then we have a look at the submission time and compile time, we see an interesting pattern that actually the malware author is actively developing something, so is compiling and then immediately is submitting his creation to our sandbox. In fact, you can see a small difference between the compile time and the submission time in the order of few minutes. Then, more interestingly, the first 2 samples were completely unknown to any antivirus company, while the last one was considered as malicious. Then, if we start having a look at the binary, the first sample is just implementing, in the main function is just calling, for example, an API just to list all the processes in a Windows system. But then, starting from the second samples, we have an additional block here in the code that is actually implementing an anti-sandbox feature. As you can see here, the author is first calling the timestamp counter register that is containing the CPU cycles. Then is invoking an API, in this case the close handle, and then is calling again the timestamp. In this way, given the fact that this particular API is hooked by the sandbox, it can detect a time discrepancy and it can detect the sandbox environment. Then the last samples is the difference between the second and the third samples is just on tuning the threshold for the time discrepancy. And it's interesting because only the last one is detected as malicious. Then another interesting case is about the Trojan dropper, Trojan dropper development. In this case, we have a cluster that is composed of 5 executables. The first 4 clusters, the first 4 samples have a compile time that is not really consistent with the submission time. But if we have a look at the submission time, it's really interesting. All the samples are submitted with a difference of a few hours. Then another interesting fact here is that the first 4 samples are written in Delphi, and the last one is written in Visual Basic. And actually, this is really weird, because during development, generally, a developer is always using the same language. Then, if we look at the binaries of the first 4 samples, they are almost the same. The only difference is about a few instructions just dealing with some thread synchronization code. Then, if we have a look at the Visual Basic, at the Visual Basic one, is the only samples that is known by an antivirus company, by antivirus companies, and is detected as a Trojan dropper. Then, if we look at the similarity between the last Delphi samples and the Visual Basic one, we can see a similarity of the 100%. So this means that then if we manually look at the samples, the Delphi samples is literally embedded inside the Visual Basic one. And then once it is executed, the Visual Basic one is dropping the Delphi executable that then turns into a code injection on a remote process. More interestingly here is that there are 2 IP addresses involved, one for the submission of the first Delphi executables, and one for the Visual Basic ones. And then if we have a look at the last IP address, at the last executable, what we notice from the report or generated by the sandbox is that the samples is using some dynamic DNS service, in our case, no IP. And if we have a look at the IP that is resolved by the DNS request, is the same one of the submitter, okay? So then this is a really interesting behavior, so we decide to have a look at this connection back behavior in our world dataset, and we discover that in general, almost 2,000 clusters share the same connection back behavior. And this is a clear indicator of some development or at least some testing. Then, okay, clearly our system is not perfect. So now let's get back at the packed binaries. Some of the proposed features can work also for the packed binaries. Unfortunately, some others not at all, like, for example, the static analysis ones. In addition, some core components, like the clusterings, need to be adapted in order to work with the packed binaries. Second, our system, okay, of course, can be easily evaded. This is true, but the malware authors has to interact with our system if he wants to know and learn the internal mechanism of our sandbox. So in the worst case, we can just observe the development of a single evasion techniques, but then by developing some more advanced methodologies, we can link the development of these evasion techniques to the first malware family that is actually implementing this bypassing, this new bypassing method. Then, in conclusion, we believe that there is valuable information inside, hidden inside the sandbox dataset. And in this paper, we just collected let's say, the low-hanging fruits, but these low-hanging fruits were more than enough to detect some really interesting cases. We hope that in the future, some other researchers will work on the same direction and will propose more advanced systems in order to detect even advanced and complex samples. And hopefully, they will be able to design a system that is able actually to detect some APT samples months and even years before they are publicly disclosed. That's all. Thank you. Thank you for your attention.
Okay, so I have one.
Done.
Once attackers know you are doing that, I mean, what kind of change they will adapt? For example, they will not submit to enablers, they will or submit few samples, or they will try to do evade your features. Can you comment on that?
Okay, so I just, okay, if the attacker is submitting, it depends on what actually the attacker is developing. So if the attacker is just developing an evasion techniques, he has to interact more than one time with our system. If the attacker instead is developing a real malware, he can interact only few times. Let's say one time, and if it's lucky enough and skilled enough, his creation can work as the first time. So let's say that for the probes, so for all the programs that interact with our sandbox, it's easier for us, I mean, to detect these creations. But for the malware development, if the attacker is motivated and smart enough, there is no reason to submit the entire malware. There is just the reason for just for the evasion techniques. That's it.
This is really interesting stuff. So when talking to somebody from the security industry, he told me that the way he would define APT, Advanced Persistent Threat, is when it looks like the software development team for the malware included a project manager. All right? So, you know, can you say something about the software development practices of the more sort of vanilla type of malware versus the ones that are more like the equation example that you gave?
Yeah, okay. First of all, we just collect all the known and available reports about the APT campaigns, and then we just have a look about if the hash was present in our dataset. And then the development that we have found in our papers are not related to the APT cases. They are two unrelated stuff. So let's say the first interesting fact is that there are some APT samples inside the dataset, but we don't have the development, or at least we were not able to detect it. Then the other interesting stuff is that there is an actual development, especially for the evasion techniques. So about the, let's say, software development for APT, we don't have any information. We just know that we have these samples there. And we detect, and we know that we have these samples there when it's too late. Like, as we can see in the first slide, we have these, here, as you can see here, I mean, we detect when it's actually really too late. Because, for example, for the APT1 is 43 months. That is more than, I think, 3 years. But we don't have the development, that's it.
Okay, so that concludes the presentation. But before you leave, there was some announcement. But let's thank the speaker one more time.
Thank you.